Good evening to all. So today we are going to discuss about the next part in the module 1, that is free vibration analysis. So that is a point which we will be discussing today. So far we have discussed about the free in the free vibration analysis. We have discussed about undamped free vibration systems in the last class, and here we will be dealing with free vibration itself, but it is damped. That is just a minute. So the general equation of motion for a damped or a dynamic system is mx double dot plus cx dot plus kx is equal to 0. So in the last class we have discussed about a condition where this is 0, that is C, that is a damping was 0, that is undamped. Now our discussion is on damped. So here, as you can see, this is a equation of a damped free vibration single degree of freedom SDOF system. So mx double dot plus cx dot plus kx is equal to 0. So the general solution for this is, I am assuming x is equal to g e raised to st. So x dot will be s into g raised to a st. This will be s square into g e raised to st. So I am substituting these things in this equation. So after substituting, I will be getting, I am taking g e raised to st as common. So in this term, this cannot be 0, this will not be 0, only the chance of 0 is on this equation. So that is ms square plus cx plus k is equal to 0. This is the equation that is similar to, you have studied in your mathematics, ax square plus bx plus c is equal to 0. Therefore the equation will be x is equal to minus b plus or minus root of b square minus 4ac by 2a, the same equation. So here instead of that we are having m, c and k. So I can write the equation solution for this is s is equal to minus c plus or minus root of b square minus 4km by 2a. So this is what we have got. Now here I am just simplifying this equation like this, that is by taking that is equal to minus c by 2m plus or minus root of, here I am taking this to the inside, so it will be c by 2m the whole square minus, this is 4k by m divided by 2m square, so it will be what, 4m square, 2 square will be there. So I will be getting cancelled and I will be getting k by m. So that is written here. So this is the generalized solution of a damped free vibration system. Generalized solution of a damped free vibration system. So that is a thing which we have obtained now. Now here now this condition, this solution can have 3 types of solutions. One is here this term c by 2m square by 2m minus k, this can be, one is this can be negative, this can be positive, and also this term it can be 0. 3 possibilities are there. Okay, so if this is negative, what will happen? C by 2m, if this has to be negative, then c by 2m and k by m, those it depend upon the values of these two. Okay, so depending on these two values, the solution can have 3 types of solutions can be there. Okay, now let us look into, so based on that, this system, that is a damped free vibration system, can be classified into over damped system, critically damped system, and under damped system. Over damped system, critically damped system, and under damped system. That is, if I am considering a graph like this, if a body is under an oscillation like this, it is going on oscillating like this, that is, there is no decrease in the amplitude. Amplitude means amplitude is given by this, this is the amplitude, this is another amplitude. So everywhere the amplitude is same, there is no change. So this is, there is no damping is there. Now in a over damped system, what will happen is that this will be this damping, it will reduce very drastically, like this it will be going. Critically damped means it will be directly from 0, it will be starting and ending soon, that is critically damped. Under damped system means the oscillation will be going on for some amount of time, that we will be looking on what is the graph. So this is the three types of conditions which can happen in a damped free vibration. So let us look into the first case, over damped system. So this is the equation, generalized equation. So to be an over damped system, this term, it should be positive. So if it should be positive means, here you can see, if it is to be positive, this root, that is c by 2m the whole square minus k by m should be greater than 0, then it will be positive. So where is that? Okay, that is, if this should be positive, how can I can rearrange to c by 2m the whole square should be greater than k by m, that is written here. So here the roots are negative and real and unequal. So here there can be two type of root s. So this solution does not, so here the solution, when I am taking into consideration, this one will be positive. So if this is positive, what will happen? Plus or minus, so the higher term will be this one, c minus c by 2m. So the roots are negative and real and they are unequal. So the solution does not contain any periodic term. So the motion is not periodic. It does not represent a vibratory motion. The two terms on the right hand represent motion which decay, and such vibrations are called overdamped system, in which the damping coefficients are very high. The damping analysis could not be considered in that type of system. That is meant by this overdamped system. So overdamped system, so mainly such type of system is very difficult to access. So it is a system, if such a system is there, does not contain any periodic term, so there is no vibratory motion, and the dynamic analysis cannot be considered. That is a overdamped system. Next is critically damped. So when it is critically damped, this c by 2m the whole square minus k by m is equal to 0. Therefore how can I write? C by 2m the whole square is equal to k by m, that is written here. This condition is known as critical damping condition. Damping coefficient, so here you can see c. So when it is under critical damped condition, this damping coefficient is known as critical damping coefficient, and it is represented as Cc. Okay, critical damping coefficient, that is a special term. Now we will be studying about some terms. So first term that we will be looking here is Cc, that is critical damping coefficient, Cc. That is critical damping coefficient, that is the first term that we will be looking on to today. And so just a minute, let me take an example. So the first term that we are studying today, extra term that we are studying today, is Cc, that is critical damping coefficient. So that will happen when the system is under critical damping. That is when it will be happening, that is c by 2m the whole square is equal to k by m. So instead of c, I am substituting c by cc by 2m is equal to root of k by m. Okay. Therefore, cc is equal to 2m into root of k by m. What is root of k by m? It is root of k by m. We have discussed in the last class or the first class itself. Here you can see. So 2m into root of k by m. So here root of k by m, it is the natural angular velocity omega. So c by cc is equal to 2m omega. You need to study these relationships. Direct questions will be asked to find out what is the cc. So maybe the k and m values will be given. We have done some problems in the last class. So similarly, the km and values will be given. From that we will be finding omega. Again multiplying that with 2m into the omega, you will be getting cc, critical damping coefficient. So like that, some small problems will be here that you should be able to do. Okay, we will be discussing that problems today itself. So that is the first term that we have studied today. Now here this is the equation. So here the solution will be, this term is completely 0. Therefore, that is why it is 0, because it is a critically damped condition. So S is equal to minus c by 2m, or S is equal to instead of c I have to substitute cc. So minus cc by 2m. So what is cc is 2m omega divided by 2m. So I will be getting S1 S is equal to minus omega. So our general equation will be like this: g1 plus g2 into t into e raised to minus omega t. That will be our general equation. That is when two roots are coming. I think in your maths you have studied, when the equations, the solutions are, the two roots are same, we will be writing like this: g1 plus g2, g1 plus g2 into t into e raised to minus omega t. So that will be our solution. So here you can see the above solution. The second term must contain t, since the two roots s1 and s2 are equal and identical. Because of the exponential term, e raised to minus omega is real, g1 and g2 must also equal to be real. Okay, that is another condition. So here now I need to find out what is g1 and g2. For that I am applying the initial condition. So initial condition is when t is equal to 0, x is equal to x0. That is, x0 means it is the initial displacement. So I am just substituting this t is equal to 0 in this equation. I will be getting g1 is equal to x0. Then the next equation is, next one it is, at t is equal to 0, x dot is equal to x0 dot. That is the initial velocity. Initial velocity. So here I have to take in order to find out x dot, I need to that is, x dot is equal to velocity, that is d by dt of x, or dx by dt. So I am just taking the differential. So I will be getting the solution like this: e raised to t into g2 minus g1 omega minus, that is, this is a term this is how it is, d by dt of a into b. So I think you know how to do that. A into b, both are containing t terms, therefore we will be getting the solution like this. So we will be getting g2 as x0 dot plus x0 omega. So I am substituting this whole thing in the final equation. So I will be getting the equation like this: x is equal to x0 into 1 plus omega t plus x dot into t the whole into e raised to minus omega t. So this will be the solution of a critically damped free vibrating system. The solution of a critically damped free vibrating system. Okay, that you have to understand in mind. We didn't start forced vibration. This is only free vibration. So when the forced vibration is coming, what will happen is that here you will be having extra terms. So you need to get idea. That is, I have already shared the notes of the last classroom. So you need to write it number of times. Then only you will be able to understand how this is been derived. Everything is solved mathematically only, that you have studied in your mathematics. So just write it 2 or 3 times, so that how the equation, the derivations, everything you need to understand. So I will just we will just go once again. So we were discussing about critically damped system. In a critically damped system, C by 2m, this should be equal to 0. So such a condition is known as critically damping, and at that critical damping the C will become Cc, that is critical damping coefficient. Once that have come, we will get another equation, Cc is equal to 2m omega. Then after that I need to find out the solution. So here we have started with S is equal to g e raised to st. This was the x is equal to g e raised to xt. This was we started. Now we have got s1 and s2 both have same roots. So if it is having the same root, our general solution will be x of t is equal to g1 plus g2 into t the whole into e raised to minus omega t. Because why, how this minus omega came? Minus omega means here our solution is e raised to st. So s is minus omega. Now we need to find, once we have got the equation, I need to find out this constant g1 and g2. For that we are applying the initial conditions. Initial condition is at t is equal to 0. When the time is 0, initial displacement is equal to x0 and initial velocity is equal to x0 dot. Nothing much have been done. So in some problems, when we are doing, you will be getting these initial velocity and initial displacement may be given. So you need to substitute that and find out. For that you need to understand the general solution. So this is our general solution. So this will be the, so this critically damped condition can be expressed like this. It will be damping and at a time, at some time, the amplitude, this is a maximum amplitude, this is a initial displacement, and this is a initial velocity, that is a tangent, and at time t, since it is critically damped, it will be showing a variation like this. Okay. Next, so this figure represents the free response of a critically damped system and does not include oscillations about the zero deflection. Instead, it is simply returns to 0 asymptotically in accordance with the exponential term. So critical damping represents the smallest amount of damping for which no oscillation occurs in the free vibration response. That is the critical damping case. So in a critical damping case, the vibration will be, it will be starting from an initial displacement and it will be eventually going to 0. It will not be having another cycle. In one cycle itself, the vibration will be subsided. So that is the second case of free vibration analysis, that is this critically damped condition. Now the last case, it is under damped system. Okay, under damped system. So in the case of an under damped system, here you can see we started with 3 conditions. The first condition was, that is over damped system. So what is the case of over damped system? C by 2m minus k, c square by 2m minus k by m is greater than 0. Next one, this is equal to 0. Third one, this is less than 0. That is the thing which we are discussing now, under damped system. So here under damped system, here you can see c by 2m the whole square minus k by m is less than 0, or c by 2m is less than k by m. So roots of this equation are negative. So in this case, the value, the damping coefficient c will be less than cc. So to find the free vibration response, a new term. So in order to find the response, a new term we are introducing. It is a second new term which we are going to introduce. It is eta. Okay, this is a new term which we will be introducing, that is, which is equal to the ratio of given damping to critical damping. So the second term, so this was our first term, that is so this was our first term, critical damping. Second term which we are introducing is theta, that is a ratio of damping coefficient C to critical damping, C by Cc, that is theta. That is the second term which we are introducing today, that is equal to the ratio of the given damping to critical damping. So it is written here, theta is equal to C by Cc. We already know what is Cc, that is 2m omega. So I am just writing C by 2m is equal to eta into omega, just substituting that term. So in this equation, we have this equation. So I am substituting c by 2m by theta. So I will be getting s minus in this term. I am just substituting in place of c by 2m. Here also I am substituting. So this is the substitution which I will be getting. Now here you have another the third term. So here you can see s is equal to minus theta into I into root of, I am just taking the negative of that, k by m minus theta the whole square, just rearranging this. Okay, nothing new, just rearranging this. Now this is known as omega d, that is the damped angular frequency, omega d. So the third term which we will be introducing today is omega d. So we have studied out omega. Omega was just root of k by m. Now the next term it is damped angular velocity. Damped angular velocity. So omega d is given by root of k by m, whole root of k by m minus theta by omega the whole square. So here the free vibration response of the damped system. So so here you can see, so this term, this whole term is now replaced with the omega d. So how it can be written? It will be like this: minus theta into omega plus or minus I omega d. Okay. So why we are arranging all this? Because these are there are so many empirical equations which we will be using for analyzing some systems or dynamic systems. So that is the reason why you will be hearing lot of new terms, lot of terms here and there, because this is been done like that. So it is done by many empirical relationships are there. That's the reason why you need to study these so many things. Now, so here you can see that is this omega d is the damped angular frequency. Therefore, time period, the damping time period Td is equal to 2 pi by omega d. In the earlier yesterday we have studied about T is equal to 2 pi by omega. Instead of that, since it is d, the damped frequency, now it is the damping period. Okay, damped period. So another term, the fourth term which we will be introducing, it is damped period, that is 2 pi by omega d. So this is what, this is equal to root of k by m minus theta into omega the whole square. Okay, because those are the fourth term which we will be introducing today. Now this was our general equation. Now s, we have two roots, one is minus theta omega plus I omega d and minus I omega d. Now I am just expanding this, you can see here, and expanding, and I can take this as a common factor. Now g1 into e into I raised to omega dt minus I into, so here I think you know what is, if I can substitute e raised to I omega t, that is, here I will be writing, that is, this was e raised to I omega t, this can be written as cos omega t plus I sin omega t, or e raised to minus I omega t, this can be written as cos omega t minus I sin omega t. Okay, this is a common thing only. So that I am just expanding here, you can see the same thing is, this is expanded and this is expanded in the same way. Here it is omega d, so here it will also be omega d. Okay, now I am just taking the, here you can see the coefficients of omega d, cos omega d and sin omega d separately taken. So g1 plus g2 and g1 I into g1 minus g2, it is represented as a and b respectively. Again two coefficients are both. Now I need to solve for a and b. So this we have done, that is, in order to solve for a and b, I need to apply the boundary condition. The first boundary condition is at t is equal to 0, x is equal to x0. So here this is x. So when t is equal to 0, what is e raised to minus, that this one will be 1. Omega, in omega 0 is 1, cos 0 is 1, sin 0 is 0. So it will be like this. So x is equal to a, or sorry, x, so here this will be x0. So a is equal to x0, 1 we have got. Second condition, I have to take d by dt. So applying the boundary condition, I will be getting b is equal to x0 dot plus x0 into eta into omega, the whole divided by omega d. So this is similar to what we have discussed in the last class, that is let me take that also, that is so here in the, this was the last class which we have discussed. So this was the equation of a undamped free vibration, undamped. So here you can see A, we are getting x0 cos omega t plus x0 dot by omega sin omega t. The same thing only we are getting here. Here also we are getting the same equation only. Here you can see, you should be able to have a similarity. So here you can see this in the undamped free vibration, we have got a solution like this: x is equal to x0 cos omega t plus x0 dot by omega sin omega t. This was the thing which we have got in the undamped condition. So in the damped condition, what has happened? Here it is same. Here instead of x0 dot by omega, the omega have changed to omega d, and another term is there, and the whole this term is multiplied by e raised to minus eta omega t. So that is the reason why we will be the equation, the basic equation we have studied there, it will be repeated, but it will be having more additions. So once you are writing 1 or 2 times, you will be able to understand. So here then I can just find the amplitude. Amplitude will be root of x0 dot plus x0 dot, this is the whole square, a square plus amplitude p is equal to root of a square plus b square. This I can find out. Now here omega d, that is omega d is equal to root of k by m into k by m minus theta omega square. Now what is k by m? K by m is k by m, k by omega is equal to root of k by m. So k by m will be omega square. So omega square minus theta square omega square. So I will be getting omega d can be written in this way also, omega into root of minus theta square. That is another relationship. So here you can see this equation omega d, one equation is root of k by m into minus theta into omega the whole square. This can be simplified as omega d is equal to omega into root of minus theta square. What is theta square? It is the ratio of c by cc. And what is cc? Cc is equal to 2m omega. And what is omega? Omega is equal to root of k by m. So this is how the relationships will be going on. So this will be the condition of a underdamped system. So you can see here the damping, it have started like this, and as the time goes, the amplitude is being reduced to almost 0. After some time interval, this will be 0. So this is the graph of a underdamped system. So that is how you need to answer. So we have discussed about 3 types of conditions that can happen in a damped vibrating SDOF system, that is an overdamped system, critically damped system, and underdamped system. Okay. Now, and we have introduced almost 4 new terms also. So here, so let us take into example. So this is a undamped free vibration system. The damping will be like this. This will be the amplitude. The time period is equal to 2 pi by omega, figure showing that. This is a case of a critically damped system. Now here another new term is also there, the last term which we will be studying today, logarithmic decrement, that is alpha. So that is, here you can see this is the case of a undamped system. So here this is the first amplitude, let it be x1. This is the second amplitude. So logarithmic decrement means it is the natural logarithm of the ratio of two consecutive cycles. That is, if for example this is a cycle xn, this is a cycle xn plus 1, then logarithmic decrement is equal to integral of ln, it is not log, natural logarithm we are taking, ln xn by xn plus 1. Okay, ln xn by xn plus 1. So that is another term which we have introduced today, that is logarithmic decrement. That is, I will write here, that is a fifth term. The fifth term that we will be, that is lambda, logarithmic decrement. Then so this is another relationship between logarithmic decrement is xn by xn plus 1. Now this xn can be written like this, xn can be e raised to minus omega t by e raised to minus omega into t plus td. Why td has come? Because it is the time period, that is a decreasing time period. That is, this was like this, it was initially it was like this, then it is slowly decreasing and it is going to 0. So this here the time period will be this one up to this. This is the time period. Since it's a damped system, time period will be td. So xn stands for e raised to minus omega t, first amplitude, then e raised to minus omega, it's the next one. So I can write like this. So here I am just rearranging these terms and I will be getting 1 by e raised to minus eta omega td. Okay, just rearranging, you will be getting this relationship. Now if I am taking the natural logarithm of this, I will be getting ln e raised to omega, this is minus only. So this term it is ln 1 by e raised to minus eta omega into td. Now this is minus, so I can take it to the upper numerator. So e raised to theta omega into td. So this one will be theta into omega into td. Now instead of td I can substitute for different terms. So again this is another relationship that is connecting logarithmic decrement and these values. Okay, so just write it 1 or 2 times and you will be understanding. So let us we will wind up today's class with a small problem where we just to see how we are using this. Then only, otherwise you will be feeling that so many terms we have studied, and just let's look into one problem. A vibrating system consists of mass 10 kilogram. The stiffness of the spring is 240 Newton per meter. K value is given. A damper with a damping coefficient is given as 10 Newton second per meter. Determine the damping factor, natural frequency, logarithmic decrement, ratio of the successive amplitude, and number of cycles after which the initial amplitude reduced to 0. These are the things we need to find out. Let's have a look into the first one. These are the things that are given. M is given, K is given, C is given. So damping factor is theta is equal to C by Cc. Okay, what is Cc? Cc is equal to, C is already given in the question. Cc is equal to 2m omega. What is omega? Omega is given, K by m. So I can just take K by m. So 2m into root of K by, here you can see I will be getting 98 Newton second per meter. Now C by Cc is equal to 10 divided by 90, that is 0.1. So then, since this theta value is less than 1, it is under damped system. Okay, based on the theta value, when theta value is equal to 1, it is critically damped. Theta is greater than 1, it is over damped, and theta is less than 1, it is under damped. So the first we have got the damping factor. So damping factor is equal to C by Cc. Next thing, it is natural frequency. Natural frequency of the damped vibration. So what it is asked? Natural frequency of the damped vibration, that is omega d. We need to know what is omega d. So here omega is equal to root of K by m. Now once we have got omega, we have having this relationship I have written here. This is the relationship. Omega d is equal to omega into root of 1 minus theta square. Theta square we have got already. This term this term we have got it as 0.1. So just substituting, you will be getting omega d, the damped natural frequency omega d is equal to 4.875 radians per second. Okay. Second one, it is logarithmic decrement. So it is given by this relationship 2 pi into theta by root of 1 minus theta square. So you will be getting the logarithmic decrement. So what is logarithmic decrement? It is equal to ln xn by xn plus 1. This we have changed it to, by substituting the terms and all, we have changed to this one, 2 pi theta by root of 1 minus theta square. Now ratio of the successive amplitude. So already we have found out in the third step this alpha. So that is equal to ln x1 by x2. So the ratio will be, you have to take the inverse of that, inverse of natural logarithm of delta, that is delta is 0.63, the inverse you will be getting 1.88. So this is the ratio of the successive amplitude. Then fifth one, they have asked about the number of cycles after which the amplitude reduced to 25%. That is, if the initial amplitude was 0, x0, now at what will be the area where the number of amplitude reduced 25%, that is when xn is equal to 0.25 of x0. So this is the equation which we can use. Theta is equal to 1 by n ln x0 by xn. So n we have to find out, just substituting we will be getting it is 2.2 cycles. So this is a simple problem which we have used the relationships or the new terms you have studied. So please go through this the derivation. If you are not clear with the derivation of the last class which you have studied, then it will be very difficult to study this derivation. And once you have finished this derivation only, or how it is, even without knowing the derivation itself, you should have an idea. So you should write down the equations in a page in different conditions, and then you should compare the equations, what all things are adding up. So once we are starting the forced vibration, new terms will be coming, the equation, the solution will be increasing, the number of terms in the solution will be much more than that which you have seen now. Okay, so that's for today's class. So please, I have in the last 3 classes itself I have recorded the video and uploaded to you. It is for you to study, because once you know the basics only, you can study the other things from the other module also, otherwise it will be very difficult. So that's all.